Today I'm going to talk about bus protocols. Bus is kind of, I guess, sort of an antiquated term these days. This is referring to any sort of communication protocol between chips. So I grabbed this slide actually came from my old 212 slides where I was talking about how buses can be asynchronous or synchronous. The difference being that an asynchronous bus doesn't have a clock signal. It just has data and control lines, and so there's usually some sort of handshaking that has to happen between the two endpoints on the bus, between the sender and the receiver. And then a synchronous bus has a clock. Now, in terms of this course, we've already used an asynchronous protocol. We're using UART right now in Lab 1. UART is asynchronous because there's no clock signal that's sent. And instead, the endpoints agree on an internal clock speed that they both synchronize to. The downside of that, of course, is that it's a very slow protocol. You've probably realized that we're operating at 57,600 bits per second, which is really slow. Now, one of the things that's a little confusing is that in the lecture slides and in the handouts, we refer to it not as UART, but as USART, and the S actually stands for synchronous. So it might be like, well, wait a second, why is synchronous in the name if it's an asynchronous protocol? Well, it turns out that on this chip, on the ATmega328 you can optionally operate UART in a synchronous mode with a clock. But we don't do that. So we're actually using it as a UART, even though we call it a USART. So we're using it in the asynchronous mode. Now we also have two synchronous interfaces that are built into the hardware that have hardware support, hardware acceleration. And those would be, of course, USART, as I mentioned, but also SPI and I2C. I2C is also referred to as TWI, which stands for two-wire interface. And we'll be talking about both of those. Today I'm going to talk about SPI. But synchronous buses have a clock signal that is shared that the endpoints use to synchronize, to clock the data in with. And generally, synchronous protocols are going to be faster. So SPI stands for Serial Peripheral Interface. And it is a master-slave style bus where the master is generating the clock that the slave or slaves use to synchronize the data. The connection is comprised of three physical wires. So there's a clock, which is called S clock. Then there's MOSI and MISO. MOSI is master out, slave in. MISO is master in, slave out, and then there's SS, which is slave select. The basic idea is that the master can signify to a slave that it wants to communicate by asserting the slave select, which is an active low signal. So normally it's high, and so by pushing it down to ground or pulling it down to ground, you are sort of activating a link between a master and a slave. But the data is actually not transmitted until you get a clock signal that starts going after the slave select is asserted. So the clock is normally idle. So it's either high or low, and I'll talk more about that in a minute, but it's usually kind of a flat line. It's not oscillating until the master selects a slave and then initiates a transfer, right? You guys with me? So the master selects a slave, and then if the master wants, it could even wait a while after selecting the slave before it starts driving the clock. And that's important for Lab 2 because your software is actually going to control when the slave select gets asserted, but the clock won't actually start until your software starts putting data into the link, into the data register. And so the software is controlling the slave select, but the clock is being controlled by the SPI hardware. You guys with me? So you don't have to bit bang the clock. You don't have to write code that says clock high, clock low, clock high, clock low. That happens in the hardware, but you do have to explicitly control the slave select in the software. So it's kind of a hybrid between software and hardware control. Okay, now the other thing about SPI is that the master sends one bit out at a time into the slave, which is kind of like how UART works, right? UART is similar in that it is a serial interface and it sends one bit at a time from sender to receiver. But the difference is that with SPI, for every bit the master sends the slave gets to send a bit back to the master. So there's an exchange that takes place. So every bit that's transferred is actually not just sent between the master and the slave, but a bit comes back from the slave. So it's kind of an exchange of a bit, sort of, right? So the way it's set up is you could think of it like a giant shift register. And I'm not sure how much you guys talked about shift registers in 211. This is one of the things about our 211 course I don't like is that they don't cover shift registers. A shift register is when you have a set of D flip-flops that are connected in series, and so every clock signal you shift the bits down by one bit at a time. So with SPI, the bits, you have a register on the master side and on the slave side, and for every clock cycle after you select the slave and you start getting clock ticks, you get one bit that is sent from the master across the master out slave in into the slave, and then the slave sends one bit back. Now the master sends bits out from either the most significant bit to the least significant bit, or the other way around, depending on how you configure it. Now in this case, it's showing bits going from most significant bit into the slave, and the slave's most significant bit are being shifted into the least significant bit of the master. So in this case, we've got two 8-bit registers, and so after 8 clock cycles, when the slave is selected, you'll have exchanged the 8 bits that were originally in the slave into the master, and the 8 bits that were in the master will go into the slave. Does that make sense? Guys with me? Now, it doesn't necessarily need to only be 8 bits. In UART, it's sort of part of the protocol that you define how many data bits and start bits and stop bits. And the data bits are usually 8. I mean, you can do 9, but generally speaking with UART, it's an 8-bit. It's based on sending one byte at a time. With SPI, that's not part of the protocol. You can send as many bits as you want. However, in these chips, they're 8-bit chips. So the data register in the 328P chip is 8 bits. So from a software perspective, the software is sending one byte at a time into the data register that gets sent over to the slave. It gets exchanged with the slave. But in a single transaction, you can send more than 8 bits. Does it make sense? But it's from the software perspective, you're sending 8 bits at a time. Now you might say, well, wait a second, hold on. If the clock is controlled by the hardware, then that would mean that if you wanted to send more than 8 bits, you'd only have less than a clock cycle for the software to provide the next 8 bits, right, after the first 8 bits are shifted out, right? Make sense? Right? Because you'd exchange 8 bits between the master and the slave, and when that's done, if you want to send more, you better hurry up because you got to get the next 8 bits into the data register on the master side, right, before the next clock edge, right? Well, it turns out you don't have to worry so much about that because remember I said that the data is only clocked when the clock is running, right? So in SPI, you can actually, the master can hold the slave select low and stop the clock, which will effectively pause the bus. So that gives the software on the Atmel side time to send the next byte into the data register, right? You guys with me? So the slave, even though it's selected, could be like, oh, well, the clock's not going, so I'll just chill for a while, right? Until the software has time to provide the next byte into the data register. Okay? Any questions about that? Okay, so now one of the things that's, I think, probably the most confusing thing about SPI is that there are actually 4 variations on the protocol. And I don't know where this comes from, at least in terms of the timing of the signals. I don't know where this originated from. I'd be interested to know what the history of this is, because it's kind of subtle, and it's kind of to me, it's kind of a disadvantage of SPI that you have to worry about this. But if you look at the way that the timing is with the protocol, there's a parameter called the clock polarity and the clock phase. So that's C-pol and C-fa, abbreviated C-pol and C-fa. And each one of those has 2 different options. You can 0 or 1 for each one. So between the 2, there's 4 different variations on the timing. The clock polarity, C-pol, defines what the idle state of the clock is. So as I mentioned, the clock is either running or not. It's not running when a slave is not selected from the perspective of that slave, but it's also not running, well, actually, that's not entirely accurate. I shouldn't say that. But the clock can either be running or not. You could actually, if you have multiple slaves, you could be running the clock without having selected a slave, technically. But if you're not sending data to a slave, the master of that clock is not going to be oscillating the clock, right? When it's not oscillating the clock, it's idle, and when it's idle, it can either be 0 or 1, depending on the setting of C-pol, right? So if C-pol is 0, the clock is low by default, and if C-pol is 1, or low when it's idle, I should say, and when C-pol is 1, the clock is 1 when it's idle, right? You guys make sense? That makes sense? So what that means is that depending on what C-pol is, that will define what the first edge of the clock is, whether it is a falling edge or a rising edge, right? Likewise, C-fa defines when the first bit in a transaction is sampled. That can either be on the first edge or the second edge, depending on the setting of C-fa. So if C-fa is 0, then the data is assumed to have changed. When I say change, the data like reaches its final state, or is in a state, or is transitioning, I should say, 1/2 cycle before the first clock edge. So that way, when the first clock edge occurs, it will be sampled, and by that time it will have been stable for a whole clock cycle. On the other hand, if C-fa is 1, the data isn't sampled until the second clock edge. So you can see, so when C-fa, so this shows all 4 combinations. So on the top is when C-fa is 0, right? Yes. So for example, let's say C-fa is 0 and C-pol is 1, right? That means that the C-pol 1 means the clock is 1 when it's idle. The first edge is going to be a falling edge. And so on that first falling edge, you're going to sample data. You're going to sample the first bit on the first edge, right? Now you might say, well, who cares? What's the big deal? Well, the problem is that you have to make sure that if you're going to do that, the first bit will have had to been set up for before that first clock edge, right? On the other hand, if C-fa is 1, then you'll actually wait until the second clock edge, which in this case is the rising edge, right? So you'll ignore the falling edge, which is the first edge, because C-pol is 1, and you'll clock you'll sample on the first rising edge, right? And that's the only difference between the two. Now you might say, well, why do we have to care about this? Well, if you have an off-the-shelf SPI peripheral, like you buy a chip, and now you want to set up your ATmel to talk to it, you're going to have to, the ATmel allows you to tell it which of these 4 timing variations you want to follow. And so basically what that means is if you buy a peripheral off the shelf, it will tell you in its data sheet which of these timing specs it follows. So you have to set up, when you initialize the SPI hardware, you have to set it up so it matches what the peripheral expects. Otherwise, it won't work. You could miss the first bit, or you'll get corruption. You guys with me? So the goal here is to recognize that we have these 4 different, very subtle variations on the timing. So whenever you buy a peripheral, you got to look in that peripheral's data sheet, figure out which one it's expecting, and then you have to set up your chip so it matches that, right? Now, what would happen if you had multiple slaves, and the different slaves use different variations of this, and you wanted to master them all with the Arduino? Then you'd be in, or sorry, the 328. Then you'd be in trouble. I don't know if that's even possible to do that. So we got to figure out which one of these to use for the peripheral that we're using, which is going to be a 3-axis accelerometer. This is another picture of the same thing. This is from the 328P data sheet. So this shows the same thing I just showed. You can CFA 0, CFA 1. If CFA is 0 and CPOL is 1, that means your first clock edge is a falling edge. That's also your first sample, right? Likewise, if CPOL is 0, your first edge is a rising edge, and that's where your first sample will be. If CFA is 1, then you're either going to have a falling or a rising edge as your first edge, depending on CPOL, but you're going to wait until the second edge before you sample, right? The other thing too is the 328P also allows you to specify which order you're going to send the bits out of the data register. So I mentioned this picture showed each of the bits being shifted out of the master data, the data register on the master side, being shifted into the slave side, from most significant bit on the master to least significant bit on the slave. But this is also something that's configurable. You can do it either way, and there's a way that you can configure. There's a bit in the configuration, the control register for the 328P that allows you to specify which order you're sending these bits out. And again, you have to make sure that it matches what's required by the peripheral that you're talking to. It's not something that you can just decide arbitrarily. You have to make sure that it matches who you're talking to. Okay, so what about multiple slaves? I mentioned this. We may or may not get to the point where we're doing multiple slaves, but there's a couple ways that you can set up multiple slaves in SPI, which I think is kind of neat. The first option is you can take the master out slave in, and you can fan it out to all the slaves, right? So you can connect it to the master in. The master out slave in could be connected to the master out slave in of each of the slaves, right? And then you can have multiple slave selects, one for each slave. Also, the clock would also be connected to all the slaves. So notice that the master generates the clock, which is connected to these 3 guys. It's the same clock signal. The MOSI is also connected to all 3 of these guys. But you have 3 separate slave selects. So you'll only, the SPI slave that's being addressed would know it's being addressed by its own individual slave select. Does that make sense? This is why I was saying earlier that technically, in this case, you could have the clock running and a slave may ignore it if its slave select isn't asserted, right? Now the disadvantage here is that you have to have more than one slave select, and unfortunately, the chip we have doesn't support that. The hardware SPI only supports one slave select pin. But another option is you could do a daisy chain. I mentioned that the SPI is essentially a shift register. So you can connect, you can have one slave select, but then you can have the master out slave in connect to the master out slave in of the first slave, and then its master in slave out, which normally I showed before went straight back to the master, but you can have it actually daisy chain into the master out slave in of the next slave. And then so on, you can have the master in slave out of that slave connect to the master out slave in of the next slave, and the master in slave out of the last slave go back into the master in slave out of the master. So what that does is it creates a much longer shift register that involves the data from the master and all the slaves. They all get joined to get kind of concatenated together into one big shift register. Yes?
So you know how if you daisy chain too many things, you can lose a little bit of the signal power just from like adding too much load resistance?
If you fan it out, yeah.
So
not if you daisy chain. So that would be the case here. Oops, sorry. That would be the case here when you fan these guys out. Like when you have the clock and the master out, slave in, fanned out. Like when I say fanned out, I mean you have a branch off and the same signal is connected to 3 endpoints. Then you're adding all of the capacitance from these 3 guys contribute, it become the load of that signal. And so, yeah, you'll lose signal integrity there if you do that. But in this case, this actually has the advantage of you just have point-to-point connections, at least for the data. The clock, of course, the clock is still fanned out to all 3, right? So the clock still has all of the load of the 3 slaves. But the data lines are only point-to-point, right? Yes?
The slaves have to be a little smarter in the daisy chained case, right?
Yeah, I think it depends on, how many cycles you clock it for, right? So if each of these are 8 bits, right, and you clock it for 8, if you have it set up like this and you clock it for 8 cycles, then you're going to shift, the master is only going to send its data to that slave, and that slave is only going to send its data to that slave, and this one's only going to slave it to this one and this one. So, but on the other hand, if you have 4 hosts in 8 bits each, so if you clock it for 32, then they would have to be smarter because they would have to know to grab, each group of 8 bits as they pass through, right? In that sense, but. Okay, so how do you use SPI on the ATmega328? This text this is a little dense, and I apologize for that. I got this from the data sheet, and I couldn't find a way to abbreviate this without having it lose some information. But basically, as I mentioned before, the slave select, if you bring up this pinout of the board and you look for slave select, you see SS is right here, and it's connected to PB2. The PB2 is the pin that the software would drive low or to set 0 when it wants to assert the slave select, right? Sorry, my watch keeps going off, and I guess I'm getting too emotional here. Sorry. Okay, so the software will set the slave select low by putting a 0 into port B bit 2. You guys make sense, right? But by setting port B pin 2 to 0, just like you would for GPIO. The MISO and MOSI and S clock are on bits 5 down to 3 of port B, but you don't have to explicitly drive those with software as if you were bit banging. Those get controlled by the hardware. Make sense? Actually, it doesn't really make a lot of sense. I don't know why they do it that way, but they make you as the programmer control the slave select, but then the other 3 signals get controlled automatically by the hardware. Okay, so the SPI interface will remain sleeping. Oh, sorry, I got ahead of myself there. Sorry. The SS line must be handled by the software, as I mentioned. Now, so the steps that you have to follow if you want to be a master is you drive the SS line low as if it were a GPIO. That's the first step. And then you write a byte into the SPI Data Register, which is a control register. When you do that, then the hardware will snap into action. It will start oscillating the clock and shifting data out, right? So the hardware will just literally sit there and wait for somebody to set the port B pin 2 low, which could happen just you're doing other stuff with GPIO. You might just coincidentally drive that pin low. But if you do that and then write into the SPI Data Register, then the hardware knows that you as a programmer are trying to send a byte out with SPI. So it'll activate the clock at whatever speed you set it up to be, and it will shift out whatever's in the data register, and it will shift in whatever the slave sends it, which will end up in the same data register. So you'll write to the data register, and once the transaction is complete, you can then read from the data register, and you'll see what the slave has put in there for you. Okay? This is from the master side. There is also an interrupt, which you can use to have the hardware notify the software that it's done sending the byte. When the interrupt is triggered, it'll call the interrupt service routine, and once the interrupt service routine is called, then the interrupt will be cleared automatically for you. Which is different from UART. Remember, I showed in the demo last week that with UART, you have to explicitly read the UART data register or the interrupt won't clear. Remember, I mentioned that, right? So you have an interrupt for UART that will trigger when a byte is received on UART, but if you don't read that byte, then it'll just keep triggering. But in this case, that doesn't happen. It's different for SPI. SPI, you don't necessarily have to read the data register. It makes sense because at least on a transmit, maybe that's not, I have to check to see if that's also the case when you're, well, if you're the master, there's no difference really, because whenever you transmit, you also receive. So that might be why. Anyway, so there's an interrupt enable bit which you can turn on, which will trigger the interrupt. The other alternative is that you can poll and wait for the byte to be received, but it's not going to take a very long time for you to receive that byte because the SPI interface is much faster than the UART. This is going to run at 4 megabits per second as compared to 57,600 kilobits per second. So you're not going to have to wait too long after you initiate this before the transfer is complete. Okay, now once that happens, now keep in mind that as a master, you've driven the slave select low, you've asserted slave select, so as long as that's low, you've kind of have the floor, right? You have the ability to continue going or not after the first byte has been exchanged. At that point, you can either deassert the slave select, or you can grab whatever's in that register or ignore it and put a new byte in that register to send to the slave. You guys with me on that? So I didn't explain that very well. So as I mentioned, whenever you do an SPI transaction, you're exchanging a byte with the slave, right? But if your goal is to just send data to the slave and you don't really care what the slave has to say back, then you may want to disregard whatever data comes back. You may just want to send, you may just want to crap flood the slave and send it a bunch of stuff, send it a stream, right? You may not necessarily need to read what the slave sends back. It may be a don't care, right? On the other hand, you may want to send the slave a byte, which will, of course, cause you to return a byte. The slave will return a byte to you, right? But the slave may not be ready to send the data to you, its response, until the next byte, in which case you may want to send a dummy byte over to the slave so you can receive its answer in the next block of 8 bits. You guys with me? Right? So in other words, the idea that you're exchanging a byte is inherent in SPI, but sometimes the data you send or the data you receive may be a don't care. You may just want to ignore it, right? You just may want to initiate a transaction. You don't necessarily want to see, both sides of the transaction. Okay, so now if you configure the chip, the ATmega chip as a slave, it's also, now this is where it gets a little crazy, because as a master, what differentiates a master from a slave Well, the slave select on the master is connected to the same pin on the slave. So it's the same pin from the perspective of both chips. Like say if we have two ATmegas connected to one another through SPI. So the master is really just whoever drives the SS low, right? And whoever doesn't do that is going to be the slave, is going to be in the slave rule. So the idea is that, and this is a little weird, and we may not actually use the ATmega as a slave, but basically if you're a slave, you would have to put data into your SPI data register before the master initiates the transaction. You'd have to preload it. You have to pre-chamber your data, right? Now, how would you know to do that? That part's unclear, right? That would have to be figured out somehow. But you'd have to pre-chamber data in the SPI data register, and then from that point, the master could drive the slave select low, initiate the clock, and then you get an exchange. And then there is an interrupt that would still trigger on the slave that would tell it the transaction's done, and then it can grab the data from its own data register. You guys with me? Now, there's a little bit of a subtlety here. If you're using it as a slave, the register, the data register is double buffered, which means that you can read the previous byte that was shifted in there while the new byte is coming in. Whereas if you're using it as a master, you don't have that ability. But I'm not sure if that's going to become relevant or not. Yeah, and that's all we've got there. Okay, so what about the speed? I mentioned 4 megahertz. Where does that come from? You can operate since the hardware is driving the clock, it's the hardware that determines the clock rate, just like with UART. So you have to configure the SPI interface to tell it what speed you want. It says in the documentation that to ensure correct sampling, the minimum low and high period should be at least 2 CPU cycles for the SPI clock being low, and 2 CPU cycles for the SPI clock being high, which means that your clock rate can be no more than 1/4 of the SPI clock could be no more than 1/4 of the CPU clock. The CPU clock's 16 megahertz, so that means you're going to be limited to 4 megahertz on the SPI clock, meaning 4 megabits per second. Right? And why do I say that? Well, if you look at the timing diagram, you see that the data is sampled. I mentioned that the first bit could be sampled on the falling or the rising edge, right? Depending on how you have it set up. But subsequent bits are sampled once per cycle. So once you sample the first bit on either the falling or the rising edge, then all the other bits after that will be on the same edge, which means that this is a single data rate protocol, right? It's 1 bit per clock. So if it's a 4 megahertz clock, it's a 4 megabit per second throughput. However, it's kind of strange because they also support a double speed rate, which allows it to run at 8, in this case, well, it's half the clock frequency, so it would be 8 megabits per second. So I don't know why. It seems a little contradictory that they say that it's got to be 2 cycles high, 2 cycles low, when they do actually support a clock rate for SPI that's half the CPU clock rate. So I don't know. I'm not sure. I haven't figured that one out yet. But so there's this SPI Control Register, which is SPCR. Of course, to write to it, you just say SPCR equals in your code, right? The first bit, the most significant bit, is the interrupt enable, which you can set high or low, just as we did with UART and for the timer that we looked at last week. There's also an SPI enable bit, which is bit 6. You have to turn that on if you wanted to use the hardware SPI. Then there's data order, which allows you to select whether the least significant bit or the most significant bit is shifted out first. That's something that you would have to set based on what the slave is expecting, or master if you're configuring yourself as a slave. Then there's an MSTR, master slave select, so that you have to set that. So actually, yeah, you have to tell it which mode it needs to be used in. Then there's the CPOL and CFA, which are the 2 bits I mentioned that determine the timing. And then there's the last 2 bits are the speed mode. So I mentioned that there's only 2 bits of that speed mode in this register, and then there's a 3rd bit SPI2X in another register. But the SPI2X doubles the speed, but if you turn that off, then your fastest mode is going to be the F oscillator divided by 4, which is going to be 4 megabits per second with our chip. Does that make sense? Okay. Okay, then there's a status register which only has 3 bits in it. It has the interrupt flag that tell you whether the interrupt is fired or not, the write collision flag, and that's the double SPI speed flag, which in this case I don't think we're going to need. We're going to need to look at these, at least not in lab 2. Okay, and then there's the data register, which is the SPDR. This works like the UART does, and as I mentioned, this is the one that you write data into. Both the master and slave both write into this first, and then they read from it after the transaction is completed, and that's the way that the exchange is implemented. Okay, so any questions about that? That's SPI. In this lab 2, we're going to be speaking SPI to an accelerometer chip, which is the LIS3DH. LIS3DH, 3D accelerometer. It's a small form factor chip. You have X, Y, and Z acceleration. It allows you to set it up in 4 range modes. You can have it have a range of plus or minus 2G, 4G, 8G, or 16G. And it supports sampling rates from 1 hertz to 5 kilohertz. And it has the highest SPI clock it supports is 10 megahertz, which good news for us because we can run our chip at full speed, and it would be still not fast enough to exceed the limit on this chip. So we'll be talking to it at 4 megahertz. So let's think about this a minute. Okay, we have a 4 megahertz, 4 megabit per second SPI link, and we've got 3 axes that we want to read acceleration from. Each one is probably going to be
16 bits, I think.
Oh wait, 16 bits. Okay, sorry, 16 bits per acceleration value, right? Did you want to say something?
I missed the front part of that. Sorry.
Oh, okay. Oh, so there's three axes, 16 bits per axis if you read a value, acceleration value, right? So that's 3 times 8. There's 24 bytes, right? And we want to read this at, 24 bits. Sorry, bits. 24 bits to read all 3. And so we want to be able, we're going to read it at 4 megahertz, right? 4 megabits per second. So it's going to be 4 million divided by 24, right? That's the fastest we could possibly read data from it. But it's only going to allow us to read at most at 5 kilohertz, or it's only going to update those acceleration values 5,000 times per second, right? I think you can read them faster than that if you want, but you're going to just be reading the same value over and over again, right?
Yeah.
All right, so the objective then is, well, we have one problem we have to solve here. We have to be able to talk to this chip from the 328P. Normally, if this were an on-chip peripheral, like if there was an accelerometer built in to the 328P, then we would just access it through control and status registers as we did for UART, the timer, GPIO, and SPI. But the problem is that this is a separate chip now. This is off-chip. So we have to talk to it through SPI, but we want to talk to it through the same sort of interface that we've been using, the control register and status register. The idea being that this chip is going to have a bunch of registers with addresses that we want to be able to read from and write to, but we're going to be doing it over SPI as opposed to be doing it through load and store instructions inside the program, right? Does that make sense? So we need to adapt the SPI into an interface where we can ask it to load or store an address, right? Well, SPI doesn't really do that, right? SPI is a shift register, right? But we have to build the load and store interface on top of SPI, right? So how's that going to work? Well, first of all, the first question is we first have to set up the actual timing parameter. So remember, we have to specify when we initialize the SPI subsystem on the 328P, we have to tell it whether we're going to be sending out the least significant bit first or the most significant bit. We have to set CPUL and we have to set CFA. The data sheet for the accelerometer does not tell you any of that. All it gives you is a timing diagram, and so you have to infer from the timing diagram what those should be. So here's the timing diagram. Now, one of the things they do that's a little annoying is they change the names of the SPI signals. They don't use MOSI and MISO and S-clock. They use SPC. I guess SPI clock. It's the first two letters of SPI and the first letter of clock, but why not just use the industry standard acronym for that? And then they use SDI for, I guess, slave data in, and SDO for slave data out. Okay, so once we get past that, now we have to figure out, okay, well, first of all, what is the CPUL? CPUL is, what is the clock when the clock is idle? Is it high or low? Well, it looks like from the timing diagram that it looks like the clock is high when it's idle.
Yeah, the top is the slate.
Sorry, that's the slate. The clock is this SPC. Yes, right. And actually, when the chip select goes down, if we want to know what the clock is when idle, we assume that it's going to be idle when the chip select is high, right? So the chip select polarity is fixed. The chip select is always active low, but the clock may be high or low when it's idle. That's what we need to figure out, right? So now technically, as I mentioned before, you can't really assume that the clock can't be running when the chip select is high, because obviously in a multi-slave setup that wouldn't necessarily be the case. But I think the implication here is that this is, in this timing diagram, this is a single slave. So if chip select, prior to the chip select dropping, we look at what the clock state is, and that's going to be our CPUL. Well, in this case, it's 1. So CPUL is going to be 1. Well, now what about CFA? CFA is the first, which clock edge after chip select is asserted, which clock edge is the first bit going to be sampled on? Well, looking at here, looking at the timing diagram here, I can see that chip select goes low, phase is 1, it drops here. So the question is, does it sample on that first falling edge? Well, we don't really know, but if you look at this abbreviation, it says TSU, setup. If you guys took my 611 class, you know what that means, setup time. The setup time is the time before you sample, right? So if they have a marking that says TSU, if the setup time begins with the first edge of the clock, that means that obviously we're not sampling on the first edge of the clock because we're setting up to sample, right? Which means that the first sample must actually happen on the next clock edge, right? Which means that CFA should be 1, right? So CPUL and CFA are both 1, 1. Next question is, well, what about, are we doing most significant bit first or least significant bit first? Well, that's pretty obvious from down here. It says MSB out and it says LSB out. So we're going to be sending the most significant bit first. So in order to set the 328P up to talk to this accelerometer, CPA, CPUL, both 1, and we're sending most significant bit first. Okay? And of course the time, it supports up to 10 megabits per second, so by setting it up for the maximum speed of 4 megabits per second, we're okay. It should be able to understand that, or it should be able to deal with that. Okay, now next question, once we figure out the timing spec, now how do we actually implement a load store style interface over SPI? See, the problem is that you have to think, like, if I'm the 328P and I want to read a status register, right? Basically, I have to tell the device, the slave, I have to say, I want to read register 12. And then the device has to access register 12 and send me the data. Well, obviously, it can't do that until it knows which address you want to access, right? Which means that you have to send the complete address to the slave before it can respond to it, right? So obviously a load instruction is going to require more than 1 byte transaction. You got to send at least 1 byte to tell it the address you want to read, and then it requires another byte to send. You got to send it a dummy byte essentially, so it can send you back its response, right? Likewise, if you want to read, you can't send the address and the data that you want to. I'm sorry, that was a read. If you want to write, you can't send the address you want to write to and the data you want to write at the same at the same time, right? You can only send 1 byte at a time. So it's going to require a 2 byte transaction for that as well. You're going to have to send it an address and send it a byte. You guys with me? So again, both read and write will have to require 2 transactions with the accelerometer. Now the other problem is there's no data bits in SPI. I mean, sorry, there is data bits. There's only data bits. There's no control bits. There's no way for me to tell it whether I'm reading or writing unless I encapsulate that inside of one of the bytes I send it, right? So, and that's exactly the way that you do it. You actually, the way it ends up looking is almost like a packet format where every transaction has to be at least 2 bytes that are exchanged. And if you look at the first byte is comprised of 8 bits, and the first 2 bits are actually control bits. The first of which being whether I want to read or write. And the second one is MS, which allows you to do multiple or single transactions. If multiple allows you to pretty much say, I want to read or write multiple addresses, so I will give you the first address, and then I will end up sending you more than 2 bytes, so I can send consecutive address accesses, reads or writes, right? So that only leaves 6 bits left over for the actual address, right? So that means that the first byte the master sends the slave is comprised of a read or write control and a multiple or single control, followed by 6 address bits, which gives you access to 64 possible registers, right, on the accelerometer. The accelerometer will send back a byte during that same transaction. What's in that byte? I don't know. Just ignore it, right? Now, if it was a read, you have to do another byte transaction, which actually you have to do during the same chip select period, the slave select, right? So you have to keep slave select asserted and have it generate another transaction, right? If it's a read, meaning that the most significant bit of the first byte that you send it, if that is a 0, that means you're writing, and if it's a 1, it means you're reading. So if it's a read, then you generate another transaction, and at which point the slave will send you back what you want to read. The question is, what do you send the slave during that second byte? Nothing. So don't care. Right? It's kind of wasted. Right? So you send it a dummy, it'll send you back the data that you want to read. If you're writing, on the other hand, then you will send it 2 bytes, the first being the address and the second byte being the data you want to write, and it will send you back nothing in both byte transactions. Right? I mean, it'll send you back something, but you can disregard it. Okay? It's like a don't care. Does it make sense? So the idea is that, essentially you've got a shift register and you're trying to build this kind of a load store interface on top of it. So this timing diagram is showing that. So So this is an example of a read or a load, reading a control register. Sorry, reading a register. I should say reading a status register. So you're going to load up your data from the 328. From your software point of view, you're going to set up a register, a variable, where the first bit will be a 1. Most significant bit will be a 1. How do you do that? We can just OR with a 1 shifted, 7 bits to the left. A second bit can be a 0, meaning single transaction. And then you're going to put in your bits, your address bits, and then you do 2 transactions. Now, as I mentioned at the beginning of the lecture, there's no way the timing diagram is going to look exactly like this, because there's no way that the Arduino, the 328P is going to be able to load the address and then initiate the second transaction without missing a beat, right? There's probably going to be a period between these 2 bytes where the clock is idle, but that's okay, right? Depending on how you write your software, I'm not sure. I would assume that there's probably going to be, because the problem is that you're going to trigger an interrupt after you send the first byte. So if that interrupt handler takes more than 4 cycles to register, then you've missed the 9th bit or the 9th bit slot, which again is okay, because you can keep, in other words, you'll keep holding this chip select low, and there'll be an idle period between the 2 byte transactions, right? Which because the C pole is 1, that idle period will have a clock of 1 there, right, between the 2 bytes. Yes.
Just a little point to add is I've implemented the SPI Read and Write for the accelerometer 2 or 3 different ways. Some had idles, some did not. They all worked exactly the same, because SPI, as long as the clock isn't going, you're good. And the only time the clock triggers is when you load data in the data register.
Yeah.
So.
Yeah, that's what tells it to go. But it knows that after 8 cycles of having done that, it'll turn it off if it's not ready to do the next byte. Okay. All right. So that's the read. There's a timing diagram here for multiple read. So if you want to read more than 1 byte, which in our case we will, because the accelerometer data is going to be 16 bits per axis, and we might want to read all 3 axes in one SPI transaction, assuming that they appear in consecutive addresses in the address space, which they do. So to do that, you would just do a regular read, and the only difference is that you would make sure that the multiple transaction bit is 1, which is going to be bit 6 in the first byte that you send over, and then the address would be the first address you want to read in numerical order, and then you would basically just keep reading the data out of the, or actually not reading it out, but setting the MDR, because remember, every time you want to receive a byte back from the slave, you have to send it a byte. So you would set 1 bit would be the address, which would be the initiation packet with the address, and tell it that you want to read and you want to do a multiple transaction, and then you can keep writing to the MDR, and every time you write to the MDR, you'll get a new byte back from the accelerometer, and those bytes will represent consecutive addresses in its memory space. So if you wanted to read all 3 axes of the accelerometer, there's 6 bytes in total, then that would require that you write 7 times. You do 7 transactions on the SPI. Make sense? All right. Now writing, I already explained this, but this shows the timing diagram for that. So if when you write, the master would write 2 bytes, at least 2 bytes. There's a multiple write version as well, but you're going to write at least 2 bytes. The first being the address, and then the second one would be the data that you want to write in there. The slave, of course, would be sending back 2 bytes, but you would ignore both. And then the multiple write allows you to write to a consecutive, just like with reads, it allows you to write to a consecutive series of addresses using the MS bit. Okay? Okay, so the acceleration data, well, the first question is, are they in consecutive addresses? They are. So there are 16 bits, so there's a high and a low component. The high is address, actually the low is address 28, the high is address 29 of the X direction, and then Y starts at 2A, goes to 2B for low and high, and then the Z axis is 2C and 2D. Okay, so all 6 of those addresses are consecutive in the address space. Now there's also this who am I register, which is at address F, and that is supposed to identify. It's kind of like a product ID, right, for the chip, and it's always supposed to return 33, and it's a read-only address. So that's a good way to test to see if you have a connection, right? To test it's a way to read a word from the accelerometer with a known content, right? Which is a good way to test it. Because the acceleration data, you don't really know, you're not going to know what to expect when you start reading that initially. Okay, so there's also some control registers that you have to be aware of. Now I didn't list them all. We have the data sheet on Dropbox, which has all the registers. I only listed the ones which I think are relevant to the project. So the first one is, and unfortunately I don't like this, but they named them Control Register 1, Control Register 2, all the way up to Control Register 6. So they did not give these registers very descriptive names. So in order to figure out what they do, you have to just look up the description. Control Register 1 has has a data rate selection, which is 4 bits. And the table here is ODR. So the table is here. So it can be, if it's 0, 0, 0, it's in power down, and then you can set it from a speed of 1 hertz all the way up to 5 kilohertz. Right? You can just set those 3 bits according to that table, and those are in the 4 bits, and those are in the 4 most significant bits of Control Register 1. There's also enable bits for each of the 3 axes that are in the least significant 3 bits. And in our case, we're going to want to turn all 3 on for the project. Although I haven't talked about the project yet, but the idea is going to be to measure all 3 of these acceleration axes. And then there's a low power enable, which we're not going to use for the project. We will disable that. It's kind of interesting, though, if you look at this. Actually, it's funny. If you want to use the fastest speed, 5 kilohertz, you have to be in low power mode. Because if you're in normal mode, it only goes up to 1.25 kilohertz, which I think is kind of interesting. You would expect the low power mode to be a slower speed than the normal mode.
What does low power mode do then?
I don't know off the top of my head. Philip, do you know? Yeah, it could be, but it's funny. I think it's funny that only in low power mode can we hit the 5 kilohertz, but that would make sense if you're only doing it for 1 axis instead of all 3. Okay, then Control Register 2 I skipped. We move on to Control Register 3. So this part is a little confusing. So there's an interrupt output from the chip that goes back to that can optionally go back to the 328P, your processor. In our case, we just wired it directly to the hardware interrupt in 0, right? So the idea is that we're going to use the interrupt to synchronize your code with the rate at which data is being sampled from the accelerometer, right? As opposed to trying to figure out, to try to come up with or set up the timer for 5 kilohertz and then sample every 5 kilohertz. There are other things you can use the interrupt for as well, too, though. The chip actually supports detection of certain events, like if you drop it, or touch it or pick it up, which is kind of neat. But in our case, we're going to use it for timing synchronization. Did you say something, Phil?
Yeah, so the reason, as Dr. Bako said, why we care about the interrupts is you can actually pull the accelerometer and ask one of its control registers, hey, is there new data available? And you can do that, but synchronizing it up so that you pull only as much as you need to is very, very difficult. So over winter break, we got the interrupt system working on this thing, and it takes a fair bit of configuring to get it to go. So Dr. Bakos, I think you're probably going to cover all of the different registers that we're going to hit to make it all go. But this chip can potentially have interrupts fire for any of I think 8 to 10 different events. The chip has over 20 different control registers. Not all of them are named control whatever, but some of them alter its behavior. There's a set of I think about 5 to 6 registers that you have to configure certain ways to get things to work right for the labs. We'll probably end up giving you that sequence. But on this one,
those are the ones I'm covering.
Yeah,
I'm covering only the ones you need for the lab, right?
Here. So, yeah, ultimately, we're only going to use, I think, probably Data Ready 1 there out of all of these. The chip has a FIFO system as well for allowing you to buffer up data so you don't have to pull as often. That's a absolute morass of configuration settings and very difficult to use. So we're just having it signal when it's ready for new data.
Yeah, so we're going to use the Data Ready 1 interrupt.
Yep.
And I believe these other ones are just set to 0. All right, so control register 5. So we skip 4, jump to 5. This one's got the only one that we care about here is this latch interrupt request. So the idea there is we want to be able to, the interrupt should go to 1 and then should stay at 1 until we explicitly reset it, right? So we just want to turn the latch interrupt mode on. For some reason, surprisingly, the default is 0 for that, which you would think that you would want it. I mean, I'm not sure why you wouldn't want that, but the idea is that you have to give, if you're going to send an interrupt to the ATmega, you want to be able to give it time to acknowledge that interrupt, right? So, and also you don't want it to double trigger on an interrupt either. So by having the latch, it's kind of a handshake. You sets the interrupt, then you service the interrupt, you do something, you do the SPI transactions, and then you can acknowledge the interrupt, and that's the way that works.
One thing to add on there, it notes that when you do latching, the interrupt will basically get stuck forever triggered. And so one of the things you have to do when you then go to read all the registers is you'll have to read that int1 source register. Otherwise, the interrupt will never be deasserted, and the chip will never give you a, hey, I have data ready signal ever again, at least until you reboot it.
Yeah, that's the handshake. It's that you acknowledge, you say, I saw your interrupt,
Yep.
Proceed. Normal, and
It'll flip it
let
off
me know.
and then latch it again when it sees another event.
And then finally, there's a control register 6. This one is not really described in the data sheet, but there's a bit called HL active, which is basically allows you to set the interrupt to be active low. And I got this from your code. I don't know. To me, it makes no difference active low, active high, but you can set that to make it active low. If you do that, of course, you have to set up the interrupt in the ATmega also to be active low or falling edge.
I think the reason I did that was depending on how long it takes your Arduino code to get everything set up and going. If you have a rising or falling edge interrupt, you might miss that signal while you're busy setting other stuff up. And so if you intentionally yank it active low and just hold it there, the Arduino has an interrupt mode where it can sense that. And so it gives you time to potentially see, oh, data's ready, pick it up and drive everything through the interrupt system.
And then finally, this is the interrupt source that Phil mentioned earlier. So this is the source. This is what you would read to acknowledge that this is what the Arduino reads to acknowledge the interrupt, and it also allows you to query the accelerometer and ask it, why did you interrupt? What was the purpose? What was the cause of the interrupt? And so Generally, this is going to be, so there's an interrupt active bit, which you would expect to be high if it had interrupted. And then there's an X, Y, Z. Actually, it splits it up in X high, X low, Y high, Y low, Z high, Z low, which basically means there's an event that's occurred in one of those registers, which means that it's ready to give you a new acceleration value. I assume that all of those will be 1, right? Does it sample all 3 axes at the same time? They all come in at the same time, or you get them on?
I have never seen it have a mismatch. I believe when it samples, it does it on
all 3 of them. Yeah.
Time.
So you're going to expect there's going to be 6 bits. These 6 bits will be all 1 as well as the interrupt. So every time you read this, you should get a 0 and 7 ones in there. Okay, and that's it for the accelerometer. The last topic I want to talk about is pulse width modulation. I mentioned, I think, in the first lecture that this chip has the ability to read analog signals. It has an analog to digital converter, but it does not have a digital to analog converter. So if you want to output an analog signal, you use pulse width modulation to do that. Pulse width modulation is, I like to think of it as kind of a fake analog signal, in the sense that it is a digital signal, which is either 0 or VDD, but it's periodic, like a clock, and you adjust the duty cycle, meaning the percentage of the clock period that is high, you can set such that if you run the signal through a low-pass filter and you try to extract out the very low frequency components of the signal, it should be equal to the duty cycle multiplied by the voltage. So if it's a 5-volt signal and your duty cycle is 20%, meaning that every period the clock is high for 20% of this clock cycle and low for 80%, then you'd expect that to look like a 2-volt signal, right? Assuming that you're running the period is fast enough and you've tuned your filter appropriately, right? Now, in our case, we're going to be using this to connect to LEDs, to make LEDs, to adjust the brightness of an LED, as opposed to having it on or off, right? Totally on or totally off. And I'm sure a lot of you have seen this. Apple figured this out, like 10 years ago, on the MacBooks, where the LED would sort of breathe, which was a neat effect, and then everyone did that after that. But that's achieved through this pulse width modulation. But it's kind of interesting because you can actually create an arbitrary analog signal with PWM. For example, in audio, there's a type of amplifier called a Class D amplifier that literally just uses a PWM signal to create sound, right? Now the problem though is that the signal itself has these really sharp edges, really fast transitions, which puts high frequency noise into it, right? But if you can filter that noise out, then you can get a nice analog signal.
So you can filter it to like a side wave or like.
You filter it basically. You attach a you attach a capacitive signal to it that will filter out these chirps that are in there from doing that. So this is sorry. Go ahead.
Just make it smoother, basically.
Yeah, if you're using it for like an audio type application. Now in our case, we're not going to do that. We're just going to attach. See, our goal is really we're going to be changing the amplitude of these LEDs in a very, very low frequency way. And LEDs by their nature will filter out, these, high frequency components. So you can actually plug a PWM signal directly into an LED. But if you were putting it into a speaker, then you'd have to worry about conditioning the signal, after, in order to get rid of the noise that would cause if you put it into a speaker and try to play music through this, right? But yeah, like a 10%. So this shows a 10% duty cycle, 20% 25, 50, 80, and 100, right? So this would give you a range of, whatever 0 to whatever your voltage is. And you can do this on a GPIO pin, which is nice. Or there's a built-in PWM hardware that's tied to the counter inside the 328P, which is nice because then you don't have to bit bang this with software. All right. So that's PWM. So those are the 3 topics for today.